Hello, in our today's video we shall look at Newton Raphson method as a method of estimating the roots of the function f of x. We'll consider the graph f of x on the vertical axis and x on the horizontal axis. It has some curve, and the curve I'm calling it y, and I've drawn a tangent to this curve at this point. I will call that point A. At point A, the value of f of x is f of x naught, and the value of x is x naught here. And then at this point where the tangent cuts x-axis, the value of x is x1 and the value of f of x by 2. And then at this point the value of x is x naught, then the value of f of x is 0. This is the line y is equal to 0. F of x is equal to 0. The gradient of the curve is given by the derivative of that curve, dy by dx. Now for this case, our curve is y, that is why I'm saying dy by dx, but it is a graph of f of x. Instead of y, now I have f of x. We just find the derivative of f of x. At point A, and x is equal to x naught. Then if we want to get the gradient at that point, we differentiate x naught. Then the gradient of the tangent at A, we find it as change in y out of change in x. If I can take you back to the diagram, we shall have change in y, we have y2 minus y1 out of x2 minus x1. But remember here, our x2 is x naught, our y2 is the f of x naught, and our x1 here is x1, and y1 is 0. If I substitute, I end up getting f of x naught out of x naught minus x1. At point A, the gradient of the curve is equal to the gradient of the tangent. Therefore, f prime of x naught is equal to f of x naught out of x naught minus x1. If I make x1 the subject, x1 is equal to x naught minus f of x naught out of f prime of x naught. If I have x1, I can also get x2. Then instead of x naught, I will substitute x1 and I get x2. If I continue, I will use x2 to get x3, and the process continues until up to xn plus 1 equals. Now it means now before this I have xn, I have the value of xn here, then I use that value to get xn plus 1. Now that is the formula for finding the root when we are using Newton Raphson. X naught, we call it the initial approximation, and it is used to approximate x1, and x1 we can use it to approximate x2, and so on. By repeating the process, successive approximations x2, x3, x4, and so on are obtained, and each from the previous one. That is, we can get x2 from x1, and this is done until the approximation is very close to the required level of accuracy, or until the required tolerance level is met. Let's look at an example. Show that the root of 2x squared minus 6x minus 3 equals 0 lies between x equals 3 and x equals 4. B. Show that the Newton Raphson method of solving 2x squared minus 6x minus 3 equals 0 gives xn plus 1 equals 2xn squared plus 3 out of 4xn minus 6. Then C. Taking x naught at 3 as the first initial approximation, find the root correct to decimal places. We were given an equation, but I'm writing it in as a function since I know it. We are approximating the root of the function f of x is equal to 0. Now instead of 0, I'm putting f of x. Now I have that function. To find whether the root lies between x equals 3 and x equals 4, I need to find f of x, f of 3, and f of 4. F of 3, if I substitute in this equation, I get negative 3. And if I substitute f of 4 in the same equation, I get, in the same function, I get 5. Then how do we conclude? Since f of 3 times f of 4 is less than 0, there is a root between x equals 0 and x equals 4. There is change of sign. If there is change of sign here, we conclude that the root lies in between the given values. Then we proceed, we go to B. We are required to prove that the NRM method for finding the root of this equation is given by this. But remember, in the previous slides, we have our formula here. We shall use our formula here, xn plus 1 equals xn minus f of xn out of the derivative of f of xn. We have our f of x as 2x squared minus 6x minus 3. Then if I differentiate this, I will get 4x minus 6. Then now I insert my n, f of xn. I'm just inserting n as a subscript in this, and even here I insert it as a subscript because what I will use is f of xn, and inserting it first here. If you insert it here, then it will be hard to differentiate mathematically. Then the next step, I just substitute into my formula here. Xn equals, now instead of f of x, I put the value of f of xn, and I also include the value here of f prime of xn. And I find the LCM. I will have 4xn squared minus 6n, then minus 2xn squared minus 6n minus 3. The LCM is 4xn minus 6. Then I can open here the bracket. I get 4xn squared minus 6xn minus 2xn squared plus 6xn plus 3 out of 4xn minus 6. Then from there we can simplify. 4xn squared minus 2xn squared. We simplify and we get 2xn squared plus 3 out of 4xn minus 6. Proved, we've shown that it is given by that. Then lastly, here we get our tolerance limit, our tolerance level, and it is always given by a half times 10 power negative n. We are trying to get the error as we covered in the previous videos. A half times 10 power negative n. N stands for number of decimal places. Then if I get 0.005, our tolerance level or limit is 0.005. Now we've already got our equation, and we are given x naught as 3, and we have the formula. It is our task to use what we have to get the root of the equation. If I substitute x naught, I substitute and I get 3.500. Then from that step, we check the absolute error there by getting the exact value minus the approximate value. Then when I subtract these two values, 3.5 and 3, I get 0.5, and it is greater than our tolerance level. It is not close, it is greater. Then what do? We shall go ahead and use x1 to get x2. What do we do there? X1 is 3.5, and if I substitute, I get 3.4375. I also check the absolute error there by getting 3.4375 minus 3.500, and I get 0.0625. It is still greater than my tolerance level, and it is not close, it is greater. Then from that point, that means x2 is not the root. I go ahead and find and use x2 to find x3. This is x3. If I substitute x2 there, I get 3.43649. I also check the absolute error there. It is 0.00101, and this one is less than our tolerance limit, tolerance level. This value here is close. We shall use now our x3 as the root of the function of the equation f of x equals 0. But remember, we are required to write our answer correct to decimal places. Let's try to write the answer. Therefore, the root is 3.44. We've seen, we continue the process until we get the value that is close to the level of accuracy or the tolerance limit. And now it's your turn. It's your turn also to try to check what you've learned. At this point, you can pause the video and you try this question and you comment with your solution, or if you meet any challenge, feel free to ask in the comment box. Thanks for watching.